So what I am going to do is to spend time on one of the three cases. That's the high-dimensional Gaussian. And then this is a special case where the covariance matrices, they are identical. They're not just identical, they're very simple. Okay, so the covariance, they're sigma squared times the identity matrix. That is the simplest possible case that you can imagine in a high-dimensional Gaussian. So we were going to work on this case, and then what we want to do is to show you that in this situation, you will be able to find the W and W0 according to the sigmas and also the mu's. Okay, so how do we solve this problem? Well, let's start by looking at the discriminant function. The discriminant function, as we have defined, it is the log of the likelihood plus the log of the prior. The log of the likelihood will be expressed as this, and log of the prior will be expressed as that. So the three cases are when sigma I is sigma squared times identity, and then the second case would be sigma I, they share the same sigma, but they're no longer identity. The third case would be the arbitrary sigma i's, where the two Gaussians, they have two different orientations. If someone can, if we want to draw this picture, someone will realize that this sigma I equals to sigma squared times identity will sort of give us a picture like this. You have one Gaussian and then the other Gaussian. The only difference between these two will be the means. Okay, so they have two different mean locations. However, the orientation and also the shape of the two Gaussians will be identical. And they're not just identical, they will have circle. Okay, they are circle. They're exactly circles because of this diagonal matrix, identity matrix definition of the sigma I. So then when we try to define the separating hyperplane or try to construct this W vector, we know that it has to be somewhere in the middle between these two mean vectors, and then the normal vector should be somehow connecting these two means. All right, so that's something that we should have in mind before we do any calculation. Okay, so the following are just some slightly tedious algebra, but we want to go through it to understand the idea. So here is case one, where the sigma I is really sigma squared times the identity. What we really want to do is to calculate or simplify this discriminant function and then find the difference between the two discriminant functions so that eventually we can come up with the W and also the W0. Now, if you plug all these in, okay, you plug these in, what is the sigma I? Now you replace sigma I by the sigma. And so you can do a simplification here. You realize that this is sigma I, okay, is expressed in this form. And then the maximization, don't forget, this is a maximization problem eventually. So you are going to take that maximization with respect to the I. Therefore, anything that has nothing to do with your I can be dropped. It's not going to hurt your maximization at all. In this case, it will be this log of sigma. So you can just kill it, and then it will not change the maximizer. You will still find the correct I. Now, when you go to here, you realize that what is the sigma that I am assuming? Well, the sigma that I am assuming is sigma squared times the identity matrix. So I can rewrite this inner product as just 1 over 2 sigma squared. That's a scalar sigma squared. And then that will be the 2 norm of xn minus mu I. And then here you will have the log of the pi i's. Then you can expand the term. Okay, so here is a quadratic term. You just expand it. And then you realize that here you have an x squared. Again, this x squared has nothing to do with your I, so you can drop it. All right. Then eventually what you will get is the following form. Okay. So going from here to here is just some rearrangement of the terms. Then you can see the following. You have an x here, and then you have all the quantities that are associated with the x. And this will be this mu I and times this constant. So that will give you that. All right. And then anything else like this term and that term, they will go to here. Okay, so now you can see that what does this look like? This is like an apple times x plus an orange. Okay, all right. Okay, so what is it? Well, what we want to do is W transpose X plus W0. This is that form. Okay, so now what? Well, then you have GI, and of course you will have GJ. So you have two classes, the ith class and also the jth class. You take the difference between these two classes. Then what do you have? You have the apple minus the apple, you have orange minus the orange, and then you magically group the terms together with a cup of coffee. Then you will have this form. Okay, now what is this form? Well, this form says that my gx, okay, so gx is eventually the classifier that I want to know. The gx will be expressed as something in a product with x plus an offset. Okay, now what would be the normal vector? That would be mu I minus mu j. Isn't it just the picture that we want? We have two circles here, and then these are the centers, and the separating hyperplane has to be in the middle, right? And we know that the normal vector has to connect these two centers. This is exactly reflecting what we want, because here is mu 1, and this is mu 2, is mu 1 minus mu 2. That is the normal vector. Of course, you're scaling by sigma squared because of the radius of the Gaussian. But that's not important, right? The important thing is, what is the direction? The direction is mu I minus mu j. It echoes with the picture that we draw. Now, there's an offset here. This offset will, of course, determine whether you should stay in the middle or you should stay to the left or to the right. Okay? That depends on your pi's, okay? That depends on the pi's. That also depends on the sigma. So here is a summary of the results. In this, I put it into a theorem. So the theorem says that in this very special case, where your covariance matrix sigma I is indeed an identity matrix scaled by some constant sigma square, then the separating hyperplane, the thing that we cared about, it can be represented as gx equals to w transpose x plus w0 equals to 0. So that's the separating hyperplane. The w will be given by this. Okay, it will be the difference between the two means. And then the w0 will be given by this slightly more complicated quantity that involves the mean, that involves the variance, that also involves the priors. Okay, so what do you do? Well, suppose you have a data set that contains two classes. What you need to do is to find out the means. Okay, now there will be a discussion of how do we find out the mean from the data point. So suppose we can find out the means. We can also find out the variance. Okay, in this case, it would be the mu I, mu j, and also the sigma. If you can also assign a prior probability, that's up to you. Pi I and pi j, that's totally up to you. If you don't know anything, it will be half and half. You can, once you know these five quantities, then you know immediately what is the separating hyperplane. There's no need to run a stochastic gradient descent. There's no need to formulate a loss function. It's just analytic form. Okay, so that's the beauty of generative model, that you do not need to go through a lot of the components of the pipeline. Okay, not in this stage, not in the stage of constructing your classifier. In many cases, you still need to do that when you try to find the model parameters. Okay, finding the model parameters requires some work, because to find the model parameters, in a Gaussian case, it's easy, right? Because you know that the mean vector will just be the sum of all the data points divided by total number of data points. But for some other distribution, it may not be as straightforward, right? So finding the parameters will require some work, and that, in many cases, will require a gradient descent algorithm to find the solution, okay, to find the parameter. But once the parameter is found, setting up a separated hyperplane, it will be, in many cases, it will be a lot easier. Okay, so what is the geometry of this special case? Well, we have already discussed sort of like a meaning of these quantities. So I want to draw you a picture as follows. So let's recall that the normal vector is mu I minus mu j. And then there's also a W0. Now, W transpose X plus W0 is equivalent to W transpose X of X minus X0 if you want. Okay, so that always exists at X0 such that W transpose X0 will give you W0. So I can always find this this W0. And it turns out that this X0 is given by this form. Okay, so that is the offset location. Okay, so I want to express in this way to explain a few phenomena. First of all, the normal vector, as we have discussed, it will be a direction pointing from mu I to mu j. It should be mu j to mu I. Okay, so it should be like this. All right, and then so that would be a W. Now this X0. Let's look at the term here. The X0 would be a sum of mu I plus mu j divided by 2 and some other terms. Okay? Now, if for some reason, magically, your pi I equals to pi j, for example, half and half, then what will happen to this log is that you're going to take log of 1 because they are the same. If you take log of 1, this will go to 0, right? Then this entire term will be gone. Right? So if pi I equals to pi j, then this log of pi I divided by pi j will be 0. Then you don't have this term. Then what is x0? X0 will be exactly at the midpoint between the two centers. Okay? The reason why you have an offset is because of the prior. If you say that I really trust pi I more than pi j, then you are going to push the y-intercept towards pi I rather than pi j. So you say that I just for some reason I just trust this guy more. So you are going to move your separated hyperplane towards that class. Okay, so there's a very simple geometry here. This picture sort of explained everything you need to know about this classifier. Because they are circles, and therefore there's a separating hyperplane. It's just a straight line. The normal vector is joined into two centers, and then the offset will be depending on your prior distribution. Now, for the two other cases, you can imagine what will happen. In case 2, you will have a different Gaussian. Okay. However, both Gaussians are identical. So you will no longer having a circle. You will have an ellipse. Okay. You will have two ellipses. Okay. And they have the same orientation. Then what you should imagine is that when you have these two ellipses, the center will be the direction will be somehow different, and also the offset should somehow be a little bit different. But it shouldn't be too different from this scenario. What will be really, really different is case 3, where you have an arbitrary sigma. Okay, when you have an arbitrary sigma, what it turns out there is that you may not have the two circles sitting around. And then the landscape suddenly becomes a lot more complicated, that in certain cases you cannot find a W. You cannot write the expression that Gx equals to W transpose X plus W0. In some cases, you may need another term of X transpose a W matrix and X. So that will turn you into a quadratic classifier, something that we are going to see in the following lectures. Okay, so this slide just summarizes what we have discussed. So there is a normal vector here, and then it points from one center to another. There's a midpoint, and then the offset direction is also a mu I minus mu j. And so if this pi I equals pi j equals 1/2, this log will go to 0, and so you will stay in the middle. All right. Okay, so here is the reading assignment for today's lecture. I would really encourage you to take a look at this chapter in Bishop's textbook, chapter 2.3. That gives you a lot of details of the high-dimensional Gaussian. Now, another very good point to look at is this book, Doodle-Hart and Stork's Pattern Classification, chapter 2.1, 2.2, and 2.6. They have all the derivations of the Bayesian decision rules. Okay, so let me remind you where we are. So we are in the topic of linear discriminant analysis. By its name, we are going to look at linear classifiers. We are on the left-hand side of this diagram. It's called the generative method. It's a method where you want to construct a model. In our case, it's a Gaussian model. And from the Gaussian model, you are going to define the decision boundary in terms of this W transpose X plus W0. Now, the alternative approach of linear discriminant analysis is called a discriminative approach, where you look at the data sets and then just directly draw the decision boundary. That would involve logistic regression, SVM, deep neural networks, etc. Okay? So we are on here, and we want to understand the principles, the geometry, and also the performance of this method. So last time we defined this notion called the discriminant function. And for the case of a Gaussian distribution, the discriminant function will be written in this form. The discriminant function by itself, it will be written as the log likelihood plus the log of the prior, because this discriminant function is defined according to the posterior. We are interested in looking at the posterior because typically you are given some observation. You want to claim whether this data point comes from class I or class J. And so at the back of the problem, you're solving optimization by finding the class that can maximizes the posterior probability. And so the discriminant function will just be the log of the posterior. And since Bayes' theorem says that the posterior can be written as the likelihood times the prior divided by the total probability, and then the total probability has nothing to do with your I. You can drop that term. That's how we can come up with this discriminant function. For the case of Gaussian, you plug in the likelihood function, which in this case, it would be the quadratic equation involving mu I and sigma I. So these are the class parameters, class mean and class covariance. This term comes from the normalization constant. That is the log of the determinant of the covariance matrix. And here is the prior distribution, pi I. Okay, so that is a discriminant function. And then the decision rule is, of course, you check the overall discriminant function, which is gx equals to gix minus gjx. And if gx is bigger than 0, then you claim it will be class I. Otherwise, you will claim it is class J. Again, we're doing two classes, so I and J, there are only two. Literally just two classes. If you're multiple classes, you need to extend this idea to consider multiple boundaries. There are different rules of doing multi-classes. So within the context of two classes, then what you need to do is to check against this number bigger than 0 or less than 0. Now, you look at this equation and realize that everything is determined by mu I and sigma I. And so we are going to look at the three cases where sigma I, the covariance matrix, is the identity matrix, or the two classes, they share the same covariance matrix, or the two classes, they have different covariance matrices. Last lecture, we proved that the first case where the covariance matrix is identity, then you can show that the decision boundary, this Gx, can be written as this equation is a linear equation. And the reason why we can get that is that you have this Gix minus Gjx. You look at the equation previously. You plug in the Gi into this equation, put the Gj into this equation. Because you have the same sigma, and the two sigmas, they are identical to an identity matrix, you can do a lot of cancellations. That's why you will you start with a quadratic equation. This is a quadratic equation. You can simplify it to a linear equation. Okay, this happens when your sigma I is identity. Now, so at the bottom of this slide, I mentioned a couple of things. If you tell me that there are two Gaussians, and then you also tell me the model parameters, then I will return you the separating hyperplane. This is how the Bayesian decision rule runs. Okay? This is the best possible hyperplane according to the posterior distribution. The geometry of the case one is that you draw two circles. They are circles because you have the identity matrix as the covariance matrix. So we have two circles here. The centers are denoted by the mu i's and mu j's. And we know that there is a line passing from mu I to mu j. That would be the normal vector of your separating hyperplane. So you know that the separating hyperplane has to be somewhere here, and then it has to point from mu I to mu j. Now, the offset of the separating hyperplane is, of course, in the middle. And then it depends on this term. And this is the location of your y-intercept. And you see that if you don't have any term at the, let's say you don't have any pi I and pi j, you remove this term, then it's just at the middle of the two classes. But because you have mu I and mu j, they're different values, that will add to your shift. Okay? If your mu I is big, then you would lean towards mu I. If pi j is big, you will lean towards the other class. So that's the geometry of case 1. Now we are going to look at case 2. So in case 2, we are going to assume that the covariance matrices, they are no longer identity, however, they are still the same. So when this happens, you can rewrite the discriminant function as follows. So instead of you writing a sigma I, you just replace the sigma I by the sigmas. And in class I and class J, they have the same sigmas. So you look at this equation, and then we ask, can we do some simplification to this equation? And if you look at the steps that I'm having here, the first thing I do is to remove this log of the determinant of the covariance. Why can I do that? Because at the back of this optimization, I'm trying to optimize with respect to I. And since the sigma I doesn't depend on I can just drop it. Right? Okay? So now once you drop that, then you don't have the determinant to worry about. And if you look at this term, you can see that this is a quadratic equation in X and in mu. You expand it out, you get X transpose sigma inverse X plus the cross terms, and you also have the mu I, sigma inverse, and mu I. So you have 3 terms. Now, you're applying the same trick as before. Since this first term, X transpose sigma X, doesn't contain any I, because at the back of my optimization, I want to find the I. So it has nothing to do with I, so it will not influence your optimization result. You can simply drop that. And so when you drop this term, you realize that this GI, the discriminant function, can be written as follows. It will be mu I transpose sigma inverse, which essentially is just a vector. Okay? You have a vector transpose a matrix that's another vector. I just call it WI. And then you have the offset. The offset is given by this quantity. This quantity contains nothing about X. So it's a constant with respect to X. So at this point, you realize that my discriminant function is a linear function in X. Now, it is different from before, and the difference is that previously you still have the you have the identity matrix for the sigma. So if you plug that in, you realize that this if you set your sigma equals to identity, this will be gone, this will be gone, right? So it's a little bit general than before, but it's not too different from before. Now, when you try to construct the overall discriminant function, it will be the difference between GI and GJ. So when you take the difference, you have this WI and WJ, and then WI0, WJ0. These are the two scalars. You put that together, then you can see that the discriminant function G will just become sigma inverse of this mu I minus mu j, this entire vector. You take a transpose, so you can define this W. And then here will be your offset. Okay, so it is still a linear classifier. So now you can also write this equation of W transpose X plus W0 in terms of this W transpose X minus X0. So now X0 becomes your offset. So once you do that, you can see that the offset, this vector will be given by this quantity minus something. Okay. Again, for sanity check, you can put this sigma equals to identity, and you will obtain the exact same result as before. So what is the geometry of this case 2? The geometry of the case 2 can be visualized in this diagram. Previously, you have mu I and mu j. Okay, so these are the two centers. You also have mu I and mu j. However, because you have the covariance matrix, the covariance matrix is no longer a identity matrix, so you will get an ellipse. You get an ellipse rather than a circle. And then you have orientation because your ellipse is not diagonal. Okay, because if you have a diagonal a covariance matrix, then it will be either vertical or horizontal ellipse. But in general, you can have any entry in your covariance matrix that will give you the orientation. So this is the covariance matrix, and now you realize that what is the W? The W is, of course, pointing from mu I to mu j, pointing from mu I to mu j. However, there is a transformation. The transformation is given by sigma inverse. The transformation would kind of rotate your vector. Okay, so if you connect from mu I to mu j, this is the direction, right? Now, but clearly, if you just draw the orthogonal vector to this, that would be your separating hyperplane. However, that's not the separating hyperplane because we know that these two ellipses they're rotated, and we know that this black line is the correct separating hyperplane. Now there's an angle here. This angle is really measured by this transformation sigma inverse. You do the sigma inverse because you want to rotate this dotted line to this solid line. The geometry is not too different. It's just that you can imagine that you have this ellipse, but since you rotated the ellipse, this separating hyperplane has to follow your orientation. It's the exact same rule orientation. You move to the left or to the right by 50 degrees, then your separating hyperplane has to also move to the left or to the right by 50 degrees. That is the geometry. Now, the offset x0, you can see that it also contains two terms. Previously, we have this equation with this sigma equals to identity, but now you have a sigma here. But if you look at the first term, it's still the midpoint between the two centers. Okay, so that's the midpoint, and then you have an offset. This offset is controlled by this quantity. It's a little bit complicated, but never mind. It says that this will be a constant, and then there is a moving direction. There's still mu I minus mu j, so you move from here to there. Now, when do you need to take into account of this offset? It will be when pi I is not the same as pi j. When pi I is the same as pi j, you get a log of 1, that's 0, so you can just drop the term. But when they are not the same, then you need to take into account of this term. This says that, of course, okay, but looking at this equation, you realize that I'm not going to move this x0 along this direction. I'm going to move x0 along the direction suggested by mu I minus mu j. So x0 is not moving here. Okay, you won't move off this axis. You're still moving along this line from mu I to mu j. Okay, so you're just moving this line to the left or to the right. You guys see that? Right? Okay, so that is the geometry of the case 2. It's still pretty manageable. All right, but then it has a little bit more expressiveness than case 1. Case 1 is just very, very restrictive. Now let's work on case 3. Case 3 says that I have sigma 1 and sigma 2, they are both different. In this case, then the bad news is that you cannot drop the sigma I. They have to be there. Then there is limited things that you can do. The only thing you can do is to rearrange the terms in such a way that I can write down a simpler equation. So what I'm doing here is that I'm grabbing all the terms in this discriminant function. I'm just grabbing the x together. So that's a quadratic form of the x. This is a linear form of the x, and this term contains no x. Right? So I have quadratic, linear, and constant. That's for gi. Now, of course, I need to calculate the difference between gi and gj. That will give you the g. Okay? If I take the difference, since all these gi's can be written as quadratic, linear, constant, I can just take the difference between the quadratic, linear, and constant. So once you do that, then you realize what is the decision boundary? Well, you can just compute this against 0 and check whether this is bigger than 0 or it is less than 0. Now, when you look at this equation, by checking bigger than 0 or less than 0, this is just no longer linear. And so what is the separated hyperplane? You may not get a plane. Okay, the decision boundary, it could be given by a curve. So the geometry will be a lot more complicated. It's not too much complicated, but it's complicated. Okay, so now what would be the shape of your decision boundary? It really boils down to the curvature of this matrix. So you have Wi minus Wj, that is a matrix. Okay. Now, ignoring the other terms, that will be the leading term. This, if you have a positive semi-definite matrix, then you have an ellipse. If you don't, then you have some weird shape. What are the shapes? It will be like this. Okay. So there are many, many different cases. Where do I get this picture from? I got it from Wikipedia. Okay. So now, okay. So let's see. This is the easier case. This is a sphere. It happens when the W matrix is a diagonal matrix and they're all the same. All these numbers, they're the same. You get a sphere. When does it happen? Well, this happens when, for some magical reasons, when you take the difference, they become something like this. Now, it could be that one is a bigger circle, the other one is a smaller circle. So you get another circle. Okay, so that will be the geometry of the W. If you have a case like this, you have two positive numbers and then 1, 0, then one dimension is gone. So your decision boundary will be this. So you ask, where is the class 1, where is the class 2? Class 1 is inside, class 2 is outside. You can have this situation, you have two dimensions got to 0, then the decision boundary will look like this. Okay? So it will be 1 on this side, 2 on the other side. Now, of course, life are not easy, right? So you can have situations like this, like that, this, that, or that. Okay? You can have just many, many different combinations of the geometry. The good news is that when you solve a problem like this, you actually don't care how the geometry really looks like because you will never plot the diagram. What you will do on computer is that you give me a data point, x. X is your testing data point. You give me x. I just put it into my equation. This is my discriminant function. I check whether this is bigger than 0 or less than 0. Right? So you give me an image. I dump it into this classifier. I check whether the discriminant function will be positive or negative. Positive, I declare is class 1. Negative, I declare is class 0. I don't need to look at the geometry. Although it's very beautiful, it's very informative, but it doesn't help you in terms of computing. All right, so this slide summarizes what we do on computer. So the quadratic classifier is not a big deal, okay, on computer. The hypothesis, what you do is really to check whether this G is bigger than 0, less than 0, or equal to 0. So when you're given a project, okay, homework number 3, you will have the opportunity to practice this. So I will ask you to construct a Gaussian distribution from the data set, and then I will ask you to tell whether a certain data point belongs to class 1 or class 2. And the two Gaussians, they will not be the same, both in terms of the mean vector and also the covariance matrix. But don't worry, all you need to do is to construct this discriminant function and calculate this score for the testing data point. Bigger than 0, class 1, less than 0, class 2. Question? Sure. Okay, so the question is the meaning of these small w's. Okay, so the w's refers to here. There's a linear term. I call this as my w. This is my small w, and then these will be a w0. Okay, so you have 3 terms. Now the geometry, of course, it depends on all the 3 terms. So all the 3 terms. Okay, so first of all, the curvature is defined by the the Hessian, which is the W matrix. But then the linear term will move you to the left, to the right. Okay, so there's a linear term there. That will correspond to the case where W is equal to 0, W is not equal to 0. That just is the nature of the problem. Okay, so so it's just like the classical quadratic equations, right? You have ax squared plus bx plus c. Okay, so that might be a little bit easier to analyze. You ask what is the meaning of b? B is just the movement along the line. Okay, it doesn't change your curvature. Okay, so A will change your curvature, B will change your position, C will change your upper or lower. Okay, so that's the meaning of all these quantities. So it's the same thing in the high dimension, but just harder to visualize.